Okay, so our next set of videos are on systems of linear equations. So that's the next unit of study. And the first lesson is just on developing a system. So we're going to look just at developing it, and then in later lessons, we're going to look at how do I solve that system. Okay, so starting up, what is a system of equations? What does that mean? So our definition down here is two or more linear equations. And really, for our purposes, it's just going to be two linear equations. So we looked at linear equations in the previous unit. So one of them could be something like y is 2x plus 1, and that's in the form mx plus b, so that's linear. Or it could be something like 2x minus 3y plus 12 is 0. This is in the general form. Okay, and using, say, the variables x and y. So this one, I'm using x and y. This has an x, this has a y. It could be other letters, could be other variables. And our other condition here is the variables cannot have power. So I'm not going to have something like y equals x squared. This is quadratic. So it's not linear. I'm not going to have something like the square root of x plus 1 or square root of x even. This is a radical function. So this is not what we're after. We're looking at just linear functions, linear equations. So let's look at this example and see if we can develop a system of equations to model it. So it says a cashier counts $350 in 35 bills of either 10s or 20s. How many of each type of bill are there in the register? So the first thing that we want to do is define our variables. And I'm going to use x and y. You could use a and b, doesn't matter. So x, let's say x is the number of $10 bills, and y will be the number of $20 bills. All right, so that's my definition. And now, secondly, I want to write two linear equations. So now I go back and I'm going to reread the problem and decide how am I going to write those two equations. So if I look just at this piece of information, I have 35 bills. So that tells me that 35 is the number of $10 bills plus the number of 20s. So my first equation here is really just about the amount that I have. And the second equation is going to deal with the value. So $350 is $10 times every 10 that I have, plus $20 times the number of 20s that I have. And this one is more about the value. Okay, so you'll see this as a theme in some of the word problems that you'll solve, where one equation is about amount and the other one is about value. So next, we have another problem about some Boy Scouts. They're collecting cans and bottles to raise funds. Soft drink cans are worth 10 cents and bottles are worth 25. The Scouts collect 4,000 containers and earn a total of $629.50 for them. Create a linear system to model this problem. So I'm going to help you first and say that x is the number of cans and y is the number of bottles. Could I use c and b for my variables? Sure, doesn't matter. Okay, so that's my first step, the variables. What do they stand for? And then secondly, my equations. So why don't you pause the video here and try and write down your equations, see if you can get them. So hopefully you saw that this is very similar to the previous problem. I have 4,000 containers that are either cans or bottles. So this is again about the amount of them, the number of them that I have. And then the next equation is about value. So $629.50 is 10 cents times the number of cans plus 25 cents times the number of bottles. So this one is about the value. All right, and now we got an answer. It says, could the answer be that you had 2,470 cans and 1,530 bottles? Use your system to verify this answer. So verify in math means something very specific. It means I test the value in both equations. So not just in one. So in my first equation, I have 4,000 equals x plus y. And notice that this is the number of cans. Number of cans is x, and this is y. So do these add up to 4,000? And yes, they do. So it works in one equation, but I need to check in both. Very important that I show both. So that was one. My other equation is $629.50. X is 2,470 plus 25 cents times y. And let's see. Over here, this is going to be $247. And a quarter of 1,530 is $382.50. And if I add those up, I get $629.50 and $629.50. So yeah, this is the answer. So could the answer be this? Yes, that is exactly the answer. I have verified in both equations that it is correct. Okay, here's a different problem about a taxi driver. So a taxi driver charges a base fee and a fee per kilometer traveled. His first customer paid $25.75 to travel a distance of 25K, and another customer paid $39.35 to go 36. Create a linear system. So again, what I want to do is define my variables. And then secondly, I want to write my equations. So again, this might be a point to pause the video and give this one a try yourself. All right, I'm going to use the variables x and y. You may have chosen different letters, doesn't matter. And I'm going to say x is the base fee, and y is the per kilometer fee. So the first customer paid $25.75. Well, this total is the basic fee plus 25 times y. He has to pay the per kilometer fee 25 times because that's how far he went. And the second equation, 39.35 is the basic fee plus 36y. So I hope you got those two equations. Maybe you have different variables, but that's the idea there. Is it possible that he charges a base fee of $8.75 and 85 cents per kilometer? So again, what I'm asking you to do here is verify. And I verify in both equations. So basically, we're just going to check, is that the answer? So in my first equation, I would go, is $25.75 $8.75 plus 25 times 85 cents. And if I do that, I would get $8.75 plus $21.25, which is 30, which is not $25.75. So it doesn't work in the first equation. So no, this is not the answer. Just for fun, let's see if it works in the other equation. 39.35 is $8.75 plus 85 cents times 36. Which is 39.35. This one works. So that's great. That tells me that it works for this equation, but it doesn't work in this one, so it's not the answer. So even though it worked in one, it has to work in both. No, it is not the answer. It doesn't work for both. Okay? All right. Last problem here is about a sporting goods store. So in a Boxing Day sale in a sporting goods store, one customer buys 3 jackets and 2 sleeping bags for $891. If the sleeping bag is $108 more than the jacket, what is the cost of each item? So why don't you pause it here, see if you can get it, and even go all the way through to the end and see which of these, if either of them, is the right answer for your system. Okay, so again, I'm going to define my variables. I'm going to use J for jackets. And by jacket, I mean the jacket's price. Again, it's important to be specific here. I was getting a bit lazy. What does J mean? It means the price of one jacket. So I'm going to erase this and put it here properly. Define J is the price per jacket. And S isn't a great variable because it looks like a 5, but we're going to use it anyways. This is the price per sleeping bag. So now my equations, and I have to write 2, and both of them have to have J and S. So the first one is kind of easy, right? I have 3 jackets plus 2 sleeping bags is $891. So I hope you got that one. And the second one's a little bit trickier. So the sleeping bag is, now if I just translate this to an equation, the sleeping bag is, looks like that. 108 more than, what operation do you think that is? Plus the jacket. Okay, more than means plus. But if I say times more than, that's multiplication. Okay, so don't get those confused. 108 plus J. And now I put this in for jacket, this in for the sleeping bag. How did I know that? How did I know that this one wasn't the jacket and this one was the sleeping bag? Well, it says the sleeping bag is more money, so it has to be the bigger number. Okay, and when I test those, it turns out that this one does not work, but this is the answer. So I hope you saw that. And now lastly, here's kind of just one for fun about some hamburgers and fries. And this is kind of what we're working our way up to. So I have 3 hamburgers plus 2 fries is $21. 4 hamburgers plus 1 fry is $23. What's the hamburger and what's the fry?